let's get ourselves going here. 10.2a, line tangent to a circle. So that must mean we're looking at tangents today. And being able to solve different types of tangent questions today. So kind of objectives for today. We want to be able to tell if a line is tangent to a circle or not. And then talk about, okay, what different properties have to hold if in fact that line is tangent to the circle. Okay, so we've got some theorems today. Notes are going to be a little different than you're used to seeing. If you actually probably go back to kind of some of the notes you probably seen first semester, that style more today than anything. It's going to be over the next couple days. You're going to get kind of the same style as they have with notes. So that's kind of what we're looking at today. It's kind of this first little section. We've talked about this already. We've went through these to tell the difference between. So nothing here other than to just kind of a little bit of review. A chord. Remember, a chord is a segment whose endpoints lie on the circle. So we've got chord AB sitting here. Again, we've already done this. Just kind of a quick little review. It's a chord right there. Our endpoints are here and here, so we call that a chord. A secant is a line that intersects a circle in 2 points. So it intersects it here and here. We've talked about chords a little bit. We've talked about secants just a little bit. Today our main piece of it is going to be this tangent line and all the properties of the tangent line. So just remember, a tangent is a line in the same place. A line in the same place as a circle that intersects in exactly one spot. So we intersect at C. That's called a tangent line. That's the green. We were pretty good with that one when we were identifying them earlier. The point that we had trouble with was where it intersects is that point of tangency. That point of tangency is where your tangent line intersects that circle. We call that the point of tangency. Okay. And we've talked about all of these things. We just wanted to go over them real quick. But with that being said then, let's take a look at, just to remember these things, just do a quick little review, give you about a minute and a half. Why don't you go ahead and identify each line or segment that intersects point P. So name just one of the chords, name the secant, the tangent, the radii, and the diameter. Give you about a minute. Shouldn't take that long to do this one. Pirates of the Caribbean. It's that small print today. About 30 seconds left. Oh, please. In 3, 2, 1. It doesn't even beep. Oh, okay. So my chord. Which one's a chord? RQ. And we put a little segment thing over the top of it. Secant. Which one of those is a secant? SPT, or you could just say ST. Same thing. Tangent. Which one's tangent? Which one? UV or VU? A radii. There's lots of them. We'll just say PT is a radii. It's a segment, I guess. SP, QP. There's lots of those. And the diameter is ST. Kind of the same as the secant. It goes through the center this time. So those are different parts. We all okay with identifying those? That's something we did last week or earlier this week. It's all starting to run together. Okay. All right, so that leads us to our theorems for today. Our theorems for tangent lines. So one of the things we want to be able to do is we want to be able to determine if in fact it's a tangent line. And the way we determine if something's a tangent line is by using the following theorem. The theorem says if AB is tangent to circle C at point P, then AB is perpendicular to CP. So in terms that you can understand, this line, which we're calling the tangent line, is a tangent line if and only if these two lines are perpendicular to each other. Okay, and notice that this is just a radii. Okay, it's going from the center C to our point of tangency. So we can draw that line. So when it says they're perpendicular to each other, that means that this creates a right angle. So if we can somehow prove that that's a right angle, then we know that this is a tangent line. Okay, and we can start thinking of all the ways that maybe we could figure out if it's perpendicular or not. I could create a triangle here. And if I create a triangle here, maybe I can use the Pythagorean theorem if you're giving a couple things to see if that's perpendicular. When all's said and done, that has to be a 90-degree angle. If it's a 90-degree angle, that's a tangent line. If it's not 90 degrees, it's not a tangent line. Okay, we'll look at examples of how we prove this in just a second. The converse of this is also true. Remember, converses just flip the hypothesis and the conclusion. Okay, if AB is perpendicular to the radius at CP, then it is in fact a tangent. So if you're looking at a picture and that is there and says, yep, that's a 90-degree angle, I'm just flat out telling you that that's a 90-degree angle. If they flat out tell you that it's a 90-degree angle, then that has to be a tangent line to our circle. Again, whole key point in here, these two things are perpendicular to each other. If they're perpendicular to each other, then they're tangent. If they're not perpendicular to each other, then they're not tangent. Okay, so that's what the theorem says. Okay, let's look at it in practice. Okay, so the directions on here say prove that AB is a tangent to this circle. So in order to do this, if I want to prove that AB is a tangent line, this tangent line AB and this radii have to be perpendicular to each other. So that has to be a right angle. So that has to be 90 degrees. And if it's 90 degrees, then I know it's a tangent. Well, we've got a right triangle. Notice we have this triangle AB, they call it ABC. We've got this right triangle. And I erased it this morning, but we had our things that said if a squared plus b squared equals c squared, then it's a right triangle. If it's a right triangle, then that's going to be tangent. If a squared plus b squared was greater than something, it was obtuse. If a squared plus b squared is less than c squared, then it was acute, or whatever. Okay? So if I can show that a squared plus b squared does in fact equal c squared, then I know that's a right angle. If that's not true, it's not a right angle. If it's not a right angle, then they're not, AB isn't a tangent. If it is a right angle, then it is a tangent. So we got to determine which ones are our A's and B's. Which one's my A value? 8, 15, or 11?
15.
Okay, 15 is my A value. What's my B value? 8. Okay, so there's my A and my B. Now, my C value. My C value up here. What do we know about our C value? What does it have to be?
11.
Careful, let's go in general terms. What does our C have to be
8.
in the scheme of things? Don't look at this question in general. In the scheme of things, what does our hypotenuse always have to be? It has to be the longest side. It has to be the longest side. If I look up here and I say it's 11, is 11 the longest side now? No, it's not. What's going on in this problem? I think what's going on in this problem is that distance right there is 11. Is that the whole thing? No, it's not the whole thing. It's only this part of it from here to here. Do I know this distance right here?
Yes.
What is it? Not 4.
11.
What is my radius of this circle? My radius of this circle is 8, right? Is this a radius? Yes. So if my radius here is 8, this has to be 8 as well. So what is the length of this whole thing, CB? The whole thing is 19. So you have to be very careful with these questions. And this is what's going to happen with really the rest of this unit in general. You have to be careful. You have to remember properties from the past, because it's going to do things like this. It's going to put an 11 here. And you got to remember, well, 11's not bigger than 15, so that's not acting like it's my hypotenuse. What am I missing? I'm missing the radius. Well, I know the radius up here is 8, so that has to be 8. So the whole thing is 19. So you have to be careful. Now you mathematically figure it out. 15 squared. 15 squared is 225. 8 squared, I know that one, is 264. 19 squared is 361. Is 225 plus 64 361. That's 289. Does 289 equal 361? No. So is AB a tangent line? No. It has to work in order for it to be a tangent line. Since a squared plus b squared didn't equal c squared, then it was not a tangent line. It has to be a squared plus b squared equals c squared. Otherwise, it's not a tangent line. Questions with that first example? All right, let's look at the next one. Okay, so what's going through my brain is, again, we're asked if AB is a tangent line or not. Guys, let's put our computers away. You don't need them right now. Guys, put them away. Close them. You don't need them. You should be taking notes inside of, on your notes, please. Thank you. So I'm looking at this going, okay, if I know this, I need to know all the parts. I know that this is 7.5. I know my angle A, that has to be 90 degrees. I know the length of my hypotenuse is 12.5. The distance from A to my center is 5. So what's the distance from my center down to this other point? 5. Okay, so I know this has to be 5. So I'm putting it all together. Now I can use our theorem that a squared plus b squared has to equal c squared. What's the length of A? What's my A going to be? 7.5. Does it matter if I said it was 10? It doesn't. You could use either one. My b squared is 5 plus 5, which is 10. My hypotenuse is 12.5 squared. So I worked it out in my brain first. Tried to make sure I had everything that I needed. Once I had everything that I needed, then I went forward with it. So 7.5 squared, I have no idea what that is. 56.25. 10 squared, I know that's 100. 12.5 squared. 156, I think that's what I wanted it to be. 156.25. If I add 56.25, that gives me 156.25. So 156.25 equals 156.25. Is AB a transversal? Does A squared plus B squared equal C squared? Yes, it does. So therefore, this is yes. AB is a questions with that one? Question number 3. Just flip pages here a little bit. Okay, so again, we want to know if AB is a tangent line. Like I said transversal either. Why did I say transversal? I want to know if AB is a tangent line. So let's break down. Do we have everything we need? Do we know what A squared is? What's my A value? 11. So we can go 11 squared. Do we know the B value? 16. So 16 squared. Do we have the whole hypotenuse? Not as it sits right now. Okay, how did you get 20? This has to be 11 because it's a radii, right? So 11 plus 9 is 20. So then that's going to be 20 squared. So 11 squared, 121. 16 squared, 256. 20 squared is 400, I believe. 121 plus 256, I don't think that equals, that's 377. Does 377 equal 400? No. Nope. So is it a tangent line? No. Nope. It is not a tangent line. So if you're given the 3 sides, can you determine if it's a tangent line or not using Pythagorean theorem? We're okay there? Okay, now the converse said, in order for it to be a tangent line, we had to have that right triangle, right? So in the next examples, what we're going to look at is we're going to say, okay, now let's find what length that has to be in order for 9, in this case, that line to be tangent. So we're flipping it around. Before we had to use A squared plus B squared equals C squared and show that it worked. Now these questions are saying, okay, what does this length have to be in order for that to be a tangent line? So we're still going to use the Pythagorean theorem. What's my A value? 9. So we can go 9 squared. What's my B value? We don't know it, so it's our unknown, right? That's what we have to find. So we're just going to say x squared, because that's what we always use. That has to equal my hypotenuse squared. Did they give us the full length of the hypotenuse? They give us that it's 15, right? So we've got 9 squared plus x squared equals 15 squared. 9 squared is 81. X squared we don't know. 225 is 15 squared, I believe. How am I solving this equation? What do I have to do with the 81? Subtract it. So I need to move it to the other side by subtracting off 81. So that gives me x squared equals 225 minus 81, which is 144. Is that done? Now what? Take the square root. So we're going to take the square root of both sides. That gives me 12. Technically speaking, when you take the square root, it would give you positive or negative 12. But can the side length be negative? No. So our answer for this is 12. And again, you could prove it. You could go 9 squared plus 12 squared, does that equal 15 squared? And you would find out that it did. So you can always check your answers with these as well. Okay. So this is the converse of it. Okay, so that one is pretty straightforward. The next one. Okay, again, I'm taking a couple seconds to kind of figure out what's going on. Not just jumping in. I see a 2 and I know that's at the base, so it's 2 squared plus question mark squared equals 5 squared. But why can't I do that? Because what is the 2? Yeah, this whole length has to be, this is 2 as well, right? So don't just jump in. Think about it for a couple seconds. That has to be 4. So is that the hypotenuse or one of the bases? One of the bases. So 4 squared plus, I don't like question mark squared, so we'll just make it x squared equals, is that the whole hypotenuse? I think it is. So 5 squared. 4 squared is 16 plus x squared. 5 squared is, in order to solve this, we have to subtract 16 from both sides. So x squared equals 9. Probably do this one in our heads. Square root of 9 is 3. There's the value that makes that a tangent line. But again, slow down sometimes. Slow down to speed up. Don't just assume that because the numbers are there, that's what has to be done. Think about them for a couple seconds. All right, why don't you go ahead and try number 5. It's a little bit different. Not much, though. See if you can find that one. Give you about a minute. Find what question mark needs to be. Any tracksters in here? Anybody in track in here? Did we talk about this already? Didn't we? There's no tracksters in here. They're doing a mock meet today. That'd be so fun. 256, yeah. About 10 more seconds. In 3, 2, 1. All right. What's my A value? 16. Very good. So 16 squared, 8 and 8. 8 and 8 is 16. Plus x squared equals 20 squared. 16 squared, 256. X squared equals 400. Subtract 256. So x squared equals 144. I think we've seen this already. It's 12. There's our solution. All right. So our first part of our objective today was to be able to tell if something was tangent and then give a value to make it tangent. Can we do those 2 things? We're good with that? All right. Second part of today then that we're going to look at is we're going to say, okay, and these are actually, this is one of my favorite theorems in math because of the fun of the problems that we're going to have here. If you've noticed, I like to do logical things, and I like to think about things and break them down in my head that are confusing and make them a little bit easier. This theorem does that. It looks bad, and if you try to jump in, it gets confusing, but if you break it down, these are actually some of my favorite things to do. So mathematically what it says, and we got to talk theorems, it says if 2 segments with a common endpoint exterior to the circle are tangent to the circle, then the segments are congruent. You know exactly what that means, right? It's a problem with theorems. Theorems are confusing when you read them verbally. Essentially what this means. Is if I look at point A, and if I draw 2 tangent lines to 2 different points on the circle from A, that the distance from A to B is the same as the distance from A to C. These 2 pieces of each other are going to be congruent to each other. Put those tick marks. A couple things that have to happen. Great. These have to be tangent lines. They have to be tangent lines, meaning that that angle with the radius and that angle, they have to be 90 degrees. If they're not 90 degrees, this does not work. It's not a tangent anymore. So if it's not a tangent line, this doesn't hold. It has to be tangent. And now we could go through this really cool proof of why these work. We're not going to. You're just going to make the assumption that this works. That if you have a point outside of our circle, and you have two tangent lines to your circle, that those two segments always have to be the same. They always have to be the same. So if we look at some examples of this, and I think this is an easy way to kind of think about this. The directions for this say, assume that the lines appear to be tangent are tangent. Okay, so we've got this radius that's 21.1, and we've got these two what appear to be tangent lines on this. I've got a tangent line here and a tangent line here. Those are tangent to each other. So I've got a right angle there and I've got a right angle there. What this theorem says is this theorem says that this and this have to be the same length. So if this is 10, this has to be 10. If this is 20, this has to be 20. If this is smiley face, this has to be smiley face. They have to be equal to each other. Their measures are exactly the same. Well, no, we've got variables in there. Oh, no, what do I do? Well, if they're the same, that means they're equal. So if they're equal, it means that I can write the equation 4x plus 12 is equal to 5x plus 3. Is that 26.1 relevant at all to this question? No, not at all. It's just thrown in there because they told us to assume that it's a tangent line. Don't care what that 26.1 is. It's irrelevant to me. Now I have to solve the equation. So I got to get variables on one side. So I'm going to subtract 4x from both sides. And the only reason I do it that way is because I like my x value to be positive. I have to subtract 3 from both sides. 12 minus 3 is 9. I'm projecting that my x value is 9. Well, can I show that it's right? Sure. My x value is 9, so if I substitute this 9 back in here, 4 times 9 is 36. 36 plus 12 is 48. So that length with x as being 9 is 48. Well, if I put it in the other one, 5 times 9 is 45. 45 plus 3 is 48. They work. That's what my x value has to be. The measures have to be the same in order for this to work. The measures aren't the same. This does not work. So if you have equations, just set the two equations equal to each other. Those aren't the fun ones. Okay? But it works. The fun ones are ones like this, where we're asked to find everything else. These are the questions that I enjoy to do. I don't even know what the directions say. Assume that the lines are tangent. I don't even. Find the perimeter. Okay, so the directions say find the perimeter. So what does perimeter mean? Perimeter means we have to find the distance around this triangle. These triangle lines are all tangent lines. So in my brain, what I'm doing in my brain as I'm going through this problem is I'm going, okay, I've got a point right here. I've got a point, two tangent lines here and here. My thing tells me that those two have to be congruent to each other. We'll get there in a second. I'm just telling you what my brain's going through as I'm looking at the problem. I'm looking at this one, so I know that those two have to be the same. I'm looking at this one, going, these two have to be the same. All of those things have to happen, and then I can find all of those values. So if I look at this one, I know this is 12. So if that's 12, what does this have to be?
12.
It has to be 12. So I can put a 12 there.
10.4.
Okay. When I go down to this next one down here, I know this is 10.4. So this has to be,
10.4.
that has to be 10.4. But that 10.4 is just the distance from there to there. But I know this whole thing right here is 21.5. So So if I know this whole thing is 21.5, the blue line is 21.5, and I know the green line is 10.4, can I find that red line? How? Subtract. If I take the blue line, 21.5, and I subtract the green line, 10.4, that's going to give me the red line. And if I know that red line, I know that tangent line as well. 11.1? Is that what it is? Yeah. So this is my red line is 11.1. So if that's 11.1, what does this one have to be? It has to be 11.1. Okay, and if I write it with a pencil instead, that has to be 11.1. Now, what does it mean, perimeter? Perimeter means I need all of the sides. I need to know the length of each of the sides. So I got to take these parts, 12, 12, 11.1, 11.1, 10.4, and 10.4, and add them all together. That's what perimeter means. Perimeter is the distance around an object. So we have to take each of these pieces and add them together. 12 and 12 is 24. Help somebody with the calculator. I don't have it. What is it? 67? 67. Does everybody agree with that? Okay, that's why I like these. They're kind of cool. The subtraction, when we were talking about this as math teachers on Tuesday, we get together every Tuesday as geometry teachers and talk about where the problems come. This green line, blue line, red line. This is the thing that we distinguish as the biggest problem that you guys have sometimes, is how do I go from a whole if I know part of it? Remember, it's the long minus what you had equals what we need. Can you make it like 5 more minutes? Yeah. Okay, so let's look at the next one. Again, we want to look at this perimeter. We want to find the perimeter. And again, I'm stepping back and observing first. I'm not just going to jump in. I'm going to think about what do I know. Okay, I know this one is 10.4. So those two have to be the same. I know this is 8.8. Those have to be the same. I know this is 11, and those two have to be the same. So I don't know that one, but I know the whole thing, so then I can find that. So okay, now I know what I'm going to do, and I kind of have an order that I'm going to do it. So this is 10.4. This has to be 10.4. Has to be the same. This distance is 8.8. This distance has to be 8.8. This distance is 11, making this distance 11. The black line is 11. The blue line that they have is 16.8. I need to find the green. So if I go 16.8 minus 11, I get 5.8. So the green is 5.8, making this green 5.8. Now I got to do the perimeter. And I go, hey Siri, what's 5.8 plus 5.8 plus 11 plus 11 plus 8.8 plus 8.8 plus 10.4 plus 10.4? And Siri got bored with me? What would Siri get if she actually listened to me? 72? Everybody agree it's 72? Okay, take your time when you're doing these. Logically, they make sense. This is kind of why I like to do these. Logic things are kind of my thing. We okay so far? We ready to try one on your own? Okay, give you about a minute. Find the perimeter of that. About 20 seconds left. Actually, I think it says 25. That's close to 20. I'm hungry. I didn't have lunch. What did they have down there today? What was it? Is it any good? Forgot lunch today. All right. I'm just going to point to one. Tell me what it should be.
8.
Okay, that's got to be. Go away. That has to be 8. This one. Oh, I'm just going to do this. This doesn't work. So that's got to be 8 right here. 7.8. What does this one have to be? 7.2 because they have to add up 2. And they do, so that makes this one 7.2. Perimeter, add them all up.
46.
46. Everybody agree? All right. So we wanted to be able to do 2 things today before we started. We wanted to be able to show if something was tangent or not by using Pythagorean theorem, see if it worked. Can do that? Yes. We wanted to be able to find a side to make it. Can do that. And then the last part, the most fun of the day, the tangent theorem. We're good with all this? Okay. So we just had our normal worksheet day. We just had our normal notes day today. So today was a notes type of day. Tomorrow we'll come in and look at just a couple of examples. We'll do probably 1 or 2 of each of them again tomorrow to make sure that we're good to go. And then you'll get a worksheet tomorrow. There's no homework tonight. It's kind of one of those days. We got done like 13 minutes early. So we're good to go. Questions, comments, concerns, angers, griefs?